So now we've talked about two of the types of hazards. We've talked about data hazards and control hazards, and now we're going to talk about structural hazards, which are the third general type of hazards. So structural hazards occur when multiple instructions need to use the same resource in the same cycle. So that the same piece of hardware is being used by multiple instructions. And we've already seen an example of this. We saw with the register file how we needed to read and write the register file at the same time from different instructions. And the solution there was to add more hardware to double pump the register file so we could do both at the same time. Now we're going to look at two other examples of this sort of hazard. We're going to look at branch calculation and memory access. So the first example here is branch calculation hazards. Remember what we need to do when we have a conditional branch. We need to subtract two registers to see if they're equal, so we can tell if we should take the branch. And we need to calculate the branch address by adding the PC to the immediate value. So to do this, we need two ALUs. And not surprisingly, that's what we ended up building. We had one ALU to help check for equality and one ALU to do the branch calculation. So in this case, we solved the structural hazard again by adding more hardware. We added a second ALU so we could do both calculations at the same time. Let's take a look at another example. This is memory access hazards. So here's a program. We're going to start out and do a load word, then a subtraction, an addition, and another addition. And what you notice here is that in cycle 4, the load word instruction is trying to write to the data memory. The load word instruction is reading from the data memory. And at the same time, the add instruction wants to read an instruction from the memory. So we have two instructions here that are both trying to read at the same time. Two memory accesses in cycle 4, but only one memory. This is why we've been using separate instruction and data memories so far. And it's important to note here that we access the instruction memory on every cycle that we start an instruction. So we know we're going to have at least one memory read on every single cycle. So how can we solve this problem if we don't have two memories? Well, if we don't have two memories, we could put in stalls. So we could do our load word and our subtract and our add. And these are fine to have at the same time because they don't use the memory in the data memory stage. So they're not going to access the memory here, they're just going to access it when they go to load their instructions. But now we have a problem. This load word instruction that we had in the first cycle is now going to access the memory again in the fourth cycle. And so that means we can't have any other accesses there. In particular, we can't load an instruction because in this case we only have one memory. So we're going to have to put in a stall here. Now after the stall, we can go ahead and start our next instruction. But what this means is that if we only have one memory, we're going to have a lot of stalls, one stall for every time we go to access the data memory. So this is a performance issue, and we need to avoid this, and that's why we have two memories.